Okay, so just to remind you of a few things, our overall mantra, the thing that you wake up to saying every morning is energy gives rise to forces, which gives rise to motion, right? Energy gives rise to forces, which give rise to motion. Or energy gives rise to energy transfer. We transfer the energy, and we're going to start to think about how the transfer of energy is a force. If I transfer energy to Chase's face, then that's a force, right? I wouldn't do that, by the way. I would get fired if I did that, so I won't do that. But anyway, and then your face would go into motion, wouldn't it? It would go like that, right? Okay, so that's the idea. Energy gives rise to energy transfer, which gives rise to the result of energy transfer. And so far, we've talked about motion in one dimension. We've talked about motion in two dimensions. We've talked about how motion is characterized by position, displacement, velocity, acceleration. We've not talked about a whole lot else, though. We've talked about how we can describe physics in terms of language and mathematical formulas and graphs. But now we're going to start to talk about this force. How does the force give rise to a motion? How does the force give rise to a motion? And we're going to come up against a lot of misconceptions. By the way, I need all the hats off. I've been told by administration that we need to have hats off. Okay? So we're going to come up against some confusing circumstances, mostly related to the fact that we live in a world where there's friction. And what we see happen in the world around us is a result of forces acting when they're acting against friction. And so our mindset is that if I push an object, if I don't keep pushing an object, it's going to slow down, right? But if I don't have friction, if I push an object, it's going to keep going in a constant velocity forever and ever. Okay? So there's going to be a lot of misconceptions that we need to clear up. Okay, so we're going to see if we can't do that. So again, our three major themes are energy, energy transfer, and motion. I'll continue to say that. We've talked about a variety of things, and now we're already on the second page here. So we're going to begin to talk about why motion occurs. What is the nature of the transfer of energy, and how does it cause motion? And this is a branch of physics called dynamics. Okay? Things in motion are dynamics, or the study of forces. Okay, so I'm going to ask you to use your brains a little bit this morning. No. Yes. And think about a little bit of philosophy. Okay? You all have heard of Aristotle, the philosopher. Aristotle thought that the natural state of objects, whatever the object is, whether it's you, this pair of scissors, the natural state of the object is for it to be at rest. Okay? The natural state of an object is for it to be at rest, and if I want it to be in motion, I don't have to just start it to be in motion. In order to keep it in motion, I have to keep applying a force, right? And why wouldn't he think that? It's what we see every day, right? In the world around us, we see things that require us to use a force to start it in motion, and then to keep it in motion, we have to keep applying a force. If you're using your phone right now, I'd appreciate it if you put it away. Galileo came up with a different idea. Galileo, early 1600s, a little bit before Newton. He thought the natural state was to be in constant motion. And I have to clarify this. Constant motion includes a constant velocity of 0. Okay, so he didn't really consider things at rest. He considered them to be in constant motion. So if Daxton's just sitting there and he's just sitting there and he's just sitting there, he's at a constant velocity of 0 meters per second. He's in constant motion, but it's a constant motion of 0. Okay? And this is really important. In constant state of motion, whether it's 0 or non-zero, and it will continue to be it that way if no forces act on it. If no forces act on Daxton to get him to move, then he's going to continue in that motion. Okay? Now, why would something continue to be in a constant state of motion? What would it be? What property of an object would make it so that an object stayed in a constant state of motion? Why would it? Go ahead. Inertia. Okay. What do you mean by inertia? What's that? What does that mean to you when you say that?
An object at rest will stay at rest, and an object in motion will stay in motion.
Okay.
So
That's certainly true.
In motion, then it's just going to stay that way.
Okay, but what is it about the object that keeps it that way? You said inertia, but what does that really mean? Its tendency to what? If I have an object that's in a motion, it has a tendency to stay in that motion, but why does it have a tendency to stay in that motion? Its property of inertia. What does that really mean, though? It means it does what? The object does what? It resists a tendency to have its motion changed, right? If I'm a trax train, okay, and I'm traveling at a constant velocity of 30 meters per second. If I'm a trax train and I'm traveling at a constant velocity of 30 meters per second, how difficult will it be to change the motion of that trax train? Really difficult or not difficult at all? It's going to be hard to change the motion of that trax train, right? It's going to be almost impossible to change that motion unless a tremendous force is applied to it. If I'm a bicycle traveling at 30 meters per second, how difficult is it going to be to change that motion? It's traveling the same velocity as the trax train. Is it going to be easier to change the bicycle's motion or more difficult? A lot easier, right? So we have this idea, Galileo came up with this idea that there is this tendency for an object to be in constant motion, but that it resists a change in motion. And he called that change in motion, the resistance of that change in motion, inertia. What property of an object will give rise to more or less inertia? We've talked about a trax train and a bicycle. They're both traveling at the same velocity, but the trax train is more difficult to stop. It has more inertia. Why does it have more inertia? It's got more what? It's got more mass, right? So we have this nebulous property called inertia that is our tendency to resist a change in motion. Our tendency to resist a change in motion. And we recognize that that tendency to resist a change in motion is related to how much mass we have. The greater the mass, the greater the inertia. The greater the mass, the more difficult it is to change by motion. So based on those thoughts, Galileo and Newton both kind of had the same idea, but Newton put some numbers to it. Newton figured out how to calculate this, and he said every object continues in its state of rest or of uniform velocity in a straight line as long as no net force acts on it. Okay, so we have this two different philosophies, there's two sets of philosophies. One, Aristotle says, my state of being is I'm at rest, and it takes forces to move me and to keep moving me. Newton and Galileo said, I'm in constant motion, and it takes a force to change that motion. Okay, so there's two different ways of thinking about it, and Newton and Galileo obviously are the correct ones. Bottom line, an object resists change in motion, whether it's at a state of rest or at a constant non-zero velocity. And I keep going back to, and I'll keep going back to, the example of the trax train versus the bicycle, right? The trax train versus the bicycle, they're both going at the same velocity, but it's a lot more difficult to change the motion of the trax train. Or if the trax train was at zero and the bicycle was at zero, to start them in motion would take a lot more force to start the trax train in motion. And that's the idea of inertia. And inertia, for all intents and purposes, is mass. Mass is the measure of our inertia. So the measure of the degree of this resistance is mass. So the measure of this degree of resistance is mass, also known as inertia. How difficult is it to change my motion? So in order to change motion, and here's another thing that we're going to have to keep in mind. If I'm traveling at a constant velocity, my motion is not changing, both because my speed is not changing and my direction is not changing. If I am traveling at a constant velocity, I'm traveling in a straight line, and I have the same magnitude or value of that motion. If I change that motion, if I change that velocity, then that's acceleration. Okay, and remember, we said that acceleration applied to both an increase in velocity or a decrease in velocity. We tend to think of acceleration as just speeding up, but acceleration to a physicist is I could either be increasing or decreasing my velocity. Now, here's a supercritical point, and this will help us in our calculations and our analysis of these problems because it will limit the number of things that we can do. And one of the things in all of the strategies that we've always talked about is we're going to let our strategy lead us through our analysis. We're going to let our strategy lead us through how to solve the problem. And the reason that that works is because we limit our choices about what we can do. I can only do a certain thing. If I don't have time, I can only use v squared equals v0 squared plus 2a times x minus x0. If I'm traveling at a constant velocity, I can only use x equals x0 plus velocity times time. Okay, we're going to do the same thing here. In order to change motion, that is to cause an acceleration, there needs to be a net force. What do I mean by net force? It's not just a force. What do I mean by a net force? Any ideas? What's that? Yes, exactly, a combined force. Thank you, Joe. If I have an object here, and I've got a force of 10 newtons acting on it in this direction, and I've got a force of 10 newtons acting on it in this direction, and I've got a force of 10 newtons acting on it in this direction. The sum of those forces is the overall force, or the net force, okay? The sum of those forces is not 30 newtons. You would say, well, Marshall, 10 plus 10 plus 10 equals 30 newtons. But these are all acting in opposite directions, right? Okay? In fact, I've tried to draw this so that the net force is actually probably what? 0. Okay? In other words, if I have this object and it's traveling, let's say it's traveling at 10 meters per second, I've got this force and this force and this force on it. And by the way, if I've got forces that are combining to equal 0 newtons, does that mean that the object is not moving at all? No. I could put this thing in motion at 10 meters per second and then instantly apply these 3 10-newton forces, and it's still going to keep going at 10 meters per second. Okay? And that may be a little difficult to believe, but if I instantly applied all 3 of those forces at the same time, the net force is 0, so this thing's going to keep going at 10 meters per second. Okay? So the net force is the combination of these forces. Okay? But if, let's see, don't want to do that. If these other 2 forces disappeared, then I would just have the single force. And since the single force here is not balanced by anything, this object is going to continue to accelerate and accelerate and accelerate indefinitely. Okay, if I continue to apply this 10-newton force, it's going to cause this object to speed up and speed up and speed up. And it's not ever going to stop speeding up until another force is placed on it. But if I had a 10-newton force in this direction, then it would once again travel at a constant velocity, whatever that new constant velocity was. Okay? So what's going to help us then is that I only have 2 possible things that I can do here. I'm either not accelerating, in which case the forces are balanced. Okay? If I've got these 2 forces that are balanced here, this thing is not accelerating. It's traveling at a constant velocity. That's one possible state. Or it is accelerating, in which case there is a non-zero force acting on it. Okay? There's only 2 things I can do. I can either be accelerating or I'm not accelerating. And this is everything for us in analyzing our problems, and you'll see how that works. Okay? So what ends up happening then is Newton described 3 laws relating force to motion. How does force relate to motion? And we'll figure out that this is pretty much indestructible. Okay, his laws are kind of indestructible here. They've become the cornerstone of physics, and they've withstood over 300 years of experimentation and scrutiny. Okay, actually about 350 years now. Okay, and it's hard to believe that somebody 350 years ago, without computers or any advanced kind of technology, could come up with something like this. And it lasts this long. So, and we'll keep coming back to those concepts. Okay, now, this kind of, I struggle with this, the definition of a force. The definition of a force doesn't sound sciencey enough to me. The definition of a force is very simple. What is a force? It's a what? Any ideas? What's that?
Force that surrounds us and gives Jedi magic power.
Old man.
I'll go now.
What?
It gives Jedi's magic powers.
Oh, it gives Jedi's magic powers. Okay. The force. Dang. Not the force, a force. A force. Joe, do you have something to say? Okay, put your mask up over your nose. A force is a push or a pull. That's as sciencey as it gets, right? No, that's as non-sciencey as it gets. It's a push or a pull. For something as significant that rules our everyday lives the way it does, this is as simple as it gets. A force is a push or a pull. Okay? We will call a quantity of matter that has a force being exerted on it the system. Okay? And we will call the region surrounding the quantity of matter that's responsible for the force the environment. We won't pay too much attention to these definitions, but just to set some things off. Now, does the force have to be touching the quantity of matter to have an effect? Does the force have to be touching the quantity of matter? I'm touching the pen and I'm moving it around, right? I'm giving this pen motion. But if I hold it straight here, okay, and it's not moving, did the force that gave rise to that motion have to be touching the pen? No, it didn't, did it? What caused the pen to start moving? Gravity, right? So, no, it doesn't. So we can divide forces up into two broad categories: contact forces and long-range forces. Contact forces, forces that require contact between the system and surroundings in order for the force to be exerted. You know what, let's go back up here. In addition to calling that the environment, let's just call it the surroundings, because that's what I've called it below. So the surroundings. Okay? Forces that require contact between the system and surroundings in order for the force to be exerted. Okay? I listed one, a punch, right? I said if my fist comes into contact with Chase's face, that would be a contact force, right? Again, we all know that that's not going to happen.
You punch me if you want, it's really weird.
I don't want to risk it. There's no reason for me to want to anyway, so.
Thank you. I'm glad that I have me.
No, you haven't pissed me off that much yet. Okay. What other contact forces are we aware of? Just whatever.
Throwing stuff.
Throwing stuff.
Throwing a baseball or a football. Kicking a soccer ball.
Throwing stuff. Kicking stuff.
Dropping stuff.
That's not a contact force.
Grabbing under your foot.
Huh?
Grabbing under your foot.
Okay. But we're going to say that dropping stuff is a long-range force.
Grabbing.
What? Driving? That involves a contact force, doesn't it?
That's in
Piston pushing the engine. Is wind a contact force or a long-range force? What's contacting things? The air particles, yeah. Okay. What other long-range forces are we aware of? You're going to have to talk loudly because, again, I can't hear up here. What other long-range forces are we aware of? There's two other main ones.
Physical force?
So no, that's a contact force. Well, it can be gravity. It can be either. I haven't heard the words I'm looking for. If you think you've had it, yell it louder.
Electricity.
Okay.
I got it first.
Right? Two charges repel each other. Two different charges attract each other, right? What other forces of attraction are you aware of? Magnetic force. Thank you, Destin. Okay, and we'll get a chance to look at several of these different kinds of things in labs. Okay, is force a scalar quantity or a vector quantity? It's definitely one of them. Remember, scalar quantities just have a magnitude, vector quantities have magnitude and direction. So it's a vector quantity. Has both magnitude and direction, just like vector in Despicable Me. Okay. In addition to dividing forces into contact and long-range categories, there are four fundamental types of forces based on what causes the force. Gravitational force and attractive force that exists between all quantities of matter. It's the weakest of all forces. And you're like, what? If I drop off the side of a building, it's going to be a pretty strong force, right? It's going to splatter me all over the ground. Okay? But what if I tear up some little pieces of paper and put them on the table here, and then I rub a balloon on my scant amount of hair here, and then I place the balloon over the pieces of paper? Which force is going to be stronger, the electrical force or the gravity force? The electrical force, right? Because I'm going to pick up those pieces of paper with the balloon, right? The electrical force is definitely stronger than the magnetic force. And we actually call this the gravitational force. Charged particles, I'm hearing an awful lot of whispering and stuff going on, and it's driving me nuts. Charged particles at rest or in motion exert electrical forces on neighboring charged particles. In addition, they create magnetic forces on each other. Electrical and magnetic forces together are different aspects of a single electromagnetic force. Okay? These are the forces responsible for holding atoms and molecules together and what give matter their different physical properties. All contact forces are electromagnetic forces. And you're like, what? If I am pushing on this desk here, it's a force that comes from me just touching the desk, right? Not exactly. What do I know about the structure of atoms? What do I know about the structure of atoms? There's a lot of space around the outside of them, right? I've got a nucleus, and then I've got electrons in motion around the outside of the nucleus. And for these electrons that are in motion outside of the nucleus, they're, by virtue of their motion, because they're charged particles, right? How are electrons charged? Negatively, right? I've got a lot of negative charges around these nuclei, and they're generating lots of electrical and magnetic force. So if I get a bunch of atoms together here, like in the solid of this desktop and in the solid nature of my hand, these electrical fields, these electromagnetic fields, are going to interact with each other. So I'm not really touching the desk here at all. Okay, what's happening is the electromagnetic fields generated by the electrons in the atoms of my hand are interacting with the electromagnetic fields of the atoms of the desk. Okay, I'm not really contacting this. The electromagnetic fields around the atoms are what's in contact and what are interacting with each other. Okay, so when I say I have a contact force, it's not really a contact force, it's an electromagnetic force. Okay, so all contact forces are electromagnetic forces. Okay, strength of the electromagnetic force is much larger than gravitational force. Now, if I have lots of positive charges in the nucleus here, why am I going to have positive charges in the nucleus of an atom? What part? Yeah, because there's protons in the nucleus, right? So if I've got this nucleus here with all these positive charges on it, one of the things that we don't talk a lot about is that the closer like charges get together, the stronger the electrical force of repulsion. Okay? Now, when we talk about static electricity and we use a simple thing like a balloon, rubbing it in our hair to pick up pieces of paper, you don't really get the true understanding of how strong these electrical forces are. But if I place these electrical charges to within a quadrillionth of a meter to each other, okay, 1 times 10 to the negative 12 meters, if I place them that close, the force that they generate on each other is extraordinary. Okay, the amount of force that each of these protons generates on each other is unbelievably great. So hopefully it would make sense that if I've got all of these positive charges in the nucleus, that something very, very strong is going to have to hold the nucleus together. Because every one of these positive charges wants to get away from each other in the worst way. They want to repel each other with tremendous force. So to hold them together, I have to have something called the strong nuclear force. This holds the particles in the nucleus of the atoms together. It's the strongest of all of the forces, and it's hundreds of times greater than the electromagnetic force. Okay? And the force that holds these things together is intrinsic to each of these particles. These subatomic particles want to be close to each other, even though they want to repel each other at the same time, because there's also this strong nuclear force. It overcomes the force of repulsion and holds these things together. Problem with the strong nuclear force is it only acts over the distance that you find within the nucleus. Okay? It doesn't extend beyond the nucleus very far. So if I get enough of these charged particles, I create nuclei that are very unstable, and they want to destroy themselves. And those are radioactive nuclei. Okay? So the forces that are present in the nucleus are kind of in a precarious balance here. I have this incredibly strong electrical force pushing each other away, and I have this incredibly strong attractive force called the strong nuclear force that wants to hold things together. And if it's out of balance at all, we end up with radioactive things. Okay? And then we also have something called the weak nuclear force. That's a form of electromagnetic force, and it's involved in radioactive decay. The discussion of that is well beyond a high school physics class. We don't even talk about the weak nuclear force in AP physics. So that's a much more advanced topic. But we will, if we get a chance, talk a little bit more about the strong nuclear force later on. It may be that there's one basic force in the universe, and if you want to call it the force, you can, I guess, the force. And all of these things are probably just components of it. Physicists have been able to come close to mathematically explaining some forces in terms of other forces, but we haven't really completely figured out a theory that unifies all of these forces. Okay, so long-winded discussion of forces. Okay, so what did Newton tell us? What did Newton tell us? Consider a bowling ball sitting on the floor at rest. I should have brought a bowling ball, huh?
Do you have a bowling ball?
Do I have a bowling ball? Who asked that? Joe or Jet?
I asked.
Okay. There's not a person at this school that can outdo me in bowling. I have close to a 200 average.
That good?
Oh, yeah, that's really good.
Cool.
I have a 193 average.
A perfect game for what?
300. I've never rolled a perfect game, but I've come close. I've had 10 strikes in one game. I can get 12. Okay, does this bowling ball have a velocity? Does this bowling ball have a velocity? If it's just sitting there, what's its velocity? V equals 0 meters per second, right? Are there forces acting on this bowling ball? So I'm going to represent this bowling ball as a point here, and I heard somebody say gravity. The force due to gravity, Fg, F sub g, little g. Force due to gravity. So gravity is acting on this, okay? Now, how do I know that there must be another force acting on this? How do I know that there must be another force acting on this?
Because it's not boring the sand to the ground.
Okay, and what we're going to say, a lot of you will say, well, because it's not moving, but we're going to say because it's not accelerating, okay? It's not accelerating, right? It's not being pulled into the ground. It's not accelerating. And if something is not accelerating, I know there has to be no net force. In other words, there are balanced forces. So I have to know that there is another force acting on this. Otherwise, it would be accelerating, and it's not. So we have a special name for forces that are related to a surface pushing up on an object. Okay? If I have a force that's perpendicular to a surface, we call that a normal force. And the word normal here implies perpendicular. Okay, if I have a normal force, that means that that force is perpendicular to a surface. So if I'm on one of those carnival rides where you're smashed up against a wall and it's going around in a circle like this, okay, the normal force would be acting perpendicular to the object there. And we'll find out that that normal force is what keeps us traveling in a circle. That's much later on, though. Okay, so the normal force is a force that's perpendicular. If I have an object that's sitting on an inclined plane, that surface is pushing at an angle. That's also a normal force. And we're going to abbreviate that F with a big N. Okay, so gravity and a normal force are acting on this. Okay? Now, do I have forces acting in the horizontal direction? Not according to my diagram, do I? I don't have any forces acting in the horizontal direction. If I did have forces acting in the horizontal direction, because the ball is not accelerating, though, they would have to be balanced, wouldn't they? Okay, so this is called a free body diagram. We'll learn a lot more about these. A free body diagram is the motion diagram of motion. Okay? Free body diagrams are the diagrams we use for forces. Motion diagrams are the diagrams we use for motion. Now, because forces are vector quantities, we can add them together. The sum of all forces acting on an object is called the net force. And Joe reminded us of that when he said that they are the combined force, right? Another way to say that is the sum of forces. The sum of forces. So we've already stated that the key to all of this is recognizing that a net force causes accelerating, is causing acceleration. Would you say that the bowling ball is accelerating? It's not, is it? No, because why? What's happening to its velocity? It's not changing, right? We know that acceleration equals change in velocity over change in time, right? And velocity is not changing. So we want to be really precise with our explanations here. We want to say that it's not accelerating because our definition of acceleration is change of velocity, and velocity is not changing. Okay? So if we're saying the bowling ball is not accelerating, what would that say about the forces that are acting on the bowling ball? We've already said that that means they're balanced, right? There is no net force. So what's the net force on the bowling ball have to be? Has to be 0 newtons, right? Okay, so there is no net force on it. If the bowling ball was accelerating, what do you think that would say about the forces acting on the bowling ball? They're unbalanced, right? What do you think the net force on the bowling ball would be then? And this is, don't make this more complicated than it is. Very simple. It's not 0 newtons. Again, I only have two possible situations. I'm either accelerating and the net force is not 0, or I'm not accelerating and the net force is 0. If we give the bowling ball a shove, will it be accelerating while the hand is pushing the ball? And the obvious answer is yes. Okay? Why? The velocity is changing. Right? I changed it from 0 to something else. Now, if we remove the force of the hand, will the ball continue in motion? Yes. From our perspective, and I'm not trying to trick or anything, will it remain in motion at a constant velocity, continue accelerating, or slow down? It's going to slow down. Forces are still unbalanced, but now in the opposite direction. Once my hand lets go, there is no more force in the direction of motion, but what is causing force on the bowling ball? Okay, but gravity's not causing it to slow down. There's friction and air resistance, right? So we have friction and air resistance. Okay, so we've got to remember what's going on here then, because the force due to gravity is acting in a downward direction. The normal force is still acting in an upward direction, but those forces are balanced, right? I'm not accelerating in an up or down direction. Gravity and the normal force don't have anything to do with the horizontal motion here, right? Only the friction is going to be acting in the horizontal direction. So I can say I have a force of friction in the opposite direction. Okay? I don't have anything anymore in the forward direction, do I? Or the positive direction. I just have the force of friction now causing the ball to slow down. If we remove the force of the hand pushing the ball and also remove any air resistance or friction, will the ball remain in motion at a constant velocity, continue accelerating, or slow down? If I remove all friction, what's going to happen to the motion of the ball? It's going to stay at a constant velocity forever. Okay? As long as there are no forces acting on it in the horizontal direction, it's going to go on and on and on and on in a horizontal motion in a straight line at a constant velocity. And why? Because forces are, again, balanced. Okay? Forces are, again, balanced. Okay? Doesn't mean that there are no forces, it just means that the forces are balanced. If I'm traveling at a constant velocity, I might not have any forces acting on it, but if I do, they are balanced forces. So, based on this kind of a thought process and from observing and describing motions of objects on inclined planes, Galileo first speculated that if there were no friction, an object would continue to travel in motion in a straight line forever. He was the first one to pose that. Newton took this idea and developed it further, stating that an object with no net force acting on it moves at a constant velocity. And Joe recited this for this. This is the way Newton's first law is oftentimes stated. An object at rest stays at rest, an object in motion stays in motion. This is the essence of Newton's first law of motion. What I want you to think about as far as Newton's first law of motion is, though, that an object resists a change in motion. An object resists a change in motion. And the only thing that can cause a change in motion is a net force. Okay, think of the tracks train again, traveling at 30 meters per second. It wants to stay in that motion, and it will stay in that motion as long as there is no net force acting on it. Also, always remember that an object not moving is at a constant velocity of 0. So there is no state of non-motion. Okay? Aristotle got it wrong. The state of an object is not that it is not in motion. An object is always in motion. It just might be in a motion of 0 meters per second. Okay? Now, when we talk about forces acting on an object, we always have to make sure we assign direction to the forces. We always have to recognize that there are always forces of some kind acting on objects. An object can either only be accelerating or at a constant velocity. Whether an object accelerates or moves at a constant velocity depends on the sum of the forces acting on it. If the net force is 0, the object is said to be in equilibrium. The object will remain at a constant velocity. If the net force is not zero, the object will accelerate. Okay, so the way I would define Newton's first law is saying an object with no net force acting on it remains at rest or moves with a constant velocity in a straight line. It's the same thing, and you can say it however you want, as long as you incorporate the idea that an object resists a change in motion and it will require a net force to accelerate it. Okay? Now, we still have, 15 minutes. It seems like we've been talking for hours. We've covered a lot of ground here. Oh, again, the tendency of an object to resist a change in motion is called inertia. I don't want to keep on going at this point because I'm just going to keep losing more and more of you. But I do want to say the first law says an object resists a change in motion and it requires a net force to change that motion. The second law is going to say how much force is required to change the motion. So the first law says you need a net force to change motion. The second law says how much force. And I want you to recognize that you could all be Isaac Newton, okay? We all have the ability to come up with Newton's second law, because if we think about a change in motion as acceleration, okay, if we think about a change in motion as acceleration, his second law is going to say the amount of acceleration depends on how much force, okay? If I just give this a little force, I accelerate it a little, but if I give this a lot of force, I accelerate it more, right? So acceleration depends on how much force, okay? But if I put this cup of coffee on here, if I apply the same force as I did before, will I get the same amount of acceleration? No, I'll get less acceleration, right? So the amount of acceleration also depends on the mass. Now, how difficult is it to think about that based on your experience? You see this every day of your life. The stronger the force, the greater the change in motion. The greater the mass, the less the change in motion. If you put me on roller skates and you put Daxton on roller skates, and you push us both with the exact same force, which one's going to accelerate more, me or him? He's going to accelerate more, right? Because he has less mass than I do. You can tell me that I'm fat. It's okay. I get it. I have a lot of mass. Okay? I'm going to accelerate less. Okay? So that's going to be the idea. The second law says how much force causes an acceleration, how much mass relates to the acceleration. So first one says you need a net force. Second law says how much force. Okay? That's all I'm going to say about it. And you can have the last 13 minutes of class to do other things that you need to do.